At macroscopic scales, bubbles and films are governed by familiar rules of surface tension, pressure, and diffusion. A thin liquid film between two surfaces, for example, should drain and collapse, while microbubbles should dissolve quickly under Laplace pressure. Yet at the nanoscale, new forces emerge, quantum fluctuation forces, known as Casimir forces, that arise from the restless energy of the vacuum itself. These forces push or pull depending on geometry and materials, altering stability in ways that classical fluid mechanics never anticipated. Doesn't it sound uncanny that empty space might help decide whether a bubble lives or dies? The Casimir effect originates from quantum fields confined between boundaries, which restrict the wavelengths of virtual particles that can exist. The imbalance in vacuum energy produces a measurable force. Between plates, it can pull them together. Across thin films, it can shift stability. And at bubble interfaces, it could subtly change the balance of pressures. Some theorists suggest that Casimir-like contributions might help stabilize microbubbles or nanobubbles by counteracting Laplace pressure, or conversely, destabilize thin liquid films by pulling them into rupture. Could it be that the strange fluctuations of the vacuum are quietly at work inside everyday fluids? Experimental hints are tantalizing but inconclusive. Nanobubbles observed on solid surfaces often defy classical lifetimes, lasting far longer than Laplace's law predicts. Researchers usually invoke supersaturation, contact line pinning, or contamination, but some have speculated that fluctuation forces at the interface could also play a role. Similarly, ultrathin wetting films sometimes rupture at thicknesses that do not match classical predictions, raising the possibility that Casimir forces are adding a hidden hand. Isn't it fascinating that one of the deepest effects in quantum theory might leave fingerprints in something as ordinary as water? A lesser-known fact is that Casimir forces can change sign. Under certain material and geometric conditions, they become repulsive rather than attractive. If such repulsive Casimir forces act across nanoscopic voids, they could help inflate or sustain them in defiance of classical instability. The challenge is that these effects are incredibly small and difficult to measure directly in complex, noisy environments like liquids. Advanced atomic force microscopy and high-resolution optical probes may eventually reveal whether quantum vacuum fluctuations are indeed shaping bubble stability. Could microbubbles be the laboratories where cosmology's vacuum mysteries meet fluid mechanics? The paradox is that bubbles at nanoscales persist far beyond what classical theory allows, and while surface chemistry and flow may explain much, the possibility remains that quantum forces contribute as well. Out of the void itself could come stability, an invisible cushion born of fluctuations that never rest. The haunting question is whether the microbubbles we see in experiments are partly supported by quantum vacuum energy. And if so, does this mean the nothingness of space quietly sustains structures in the most unexpected corners of nature? The Casimir effect arises from quantum vacuum fluctuations, which create measurable forces between closely spaced surfaces. At nanoscales, these forces can be attractive or repulsive, depending on geometry, materials, and medium. In thin liquid films, Casimir-like pressures can add to or counterbalance classical surface tension. The effect grows as separations shrink below 100 nanometers, where vacuum energy becomes significant. For bubbles or voids, this introduces quantum contributions to stability. Instead of only Laplace pressure, Casimir forces enter the balance. This reshapes expectations of nanoscale fluid behavior. The paradox begins with vacuum energy influencing classical bubbles. Two gold plates placed nanometers apart attract due to suppressed vacuum modes between them. It is like silence itself pressing objects together because certain sounds cannot exist in the gap. Classically, thin liquid films are stabilized by van der Waals and electrostatic interactions. But Casimir forces can destabilize them by pulling interfaces together. This accelerates thinning and collapse below critical thicknesses. In some cases, films rupture sooner than expected by continuum theory. The role of vacuum fluctuations becomes apparent when observed collapse rates exceed classical predictions. Casimir-induced destabilization explains phenomena at nanometer thicknesses. This makes films fragile in ways not explained by surface tension alone. Quantum vacuum effects thus threaten classical stability. Soap films thinner than 50 am collapse faster than predicted, hinting at Casimir contributions. It is like a whisper collapsing a fragile bridge invisible to the naked eye. Conversely, Casimir forces may stabilize nanoscopic voids. Depending on geometry, quantum pressures can oppose Laplace-driven collapse. For spherical cavities in liquids, certain fluctuation modes favor persistence. This suggests that nanobubbles might partly owe stability to quantum effects. Instead of collapsing instantly, vacuum pressures act as cushions. The paradox is that the same forces that destabilize films may stabilize bubbles. Stability and instability both emerge from the same vacuum field. Quantum fluctuations rewrite interfacial physics. Theoretical models show Casimir repulsion inside cavities, balancing Laplace pressure at nanoscales. It is like invisible hands both pushing walls in and holding them apart at the same time. Microbubbles sit at the boundary between classical fluid dynamics and quantum fluctuation physics. Their size makes them subject to Laplace pressures, while their thin interfacial regions bring them into Casimir's domain. If both contributions are comparable, unexpected longevity arises. Nanobubbles that persist beyond classical dissolution times may represent quantum classical hybrids. Their behavior cannot be fully explained by either theory alone. The Casimir bubble paradox asks whether quantum vacuum stabilizes everyday bubbles. This challenges the clean separation of scales in physics. It blurs boundaries between quantum and fluid mechanics. Surface nanobubbles lasting hours contradict Laplace predictions, raising speculation of vacuum effects. It is like finding starlight influencing the flicker of a candle flame. Single bubble sonoluminescence, where bubbles emit light during collapse, invites speculation about vacuum roles. Extreme pressures and nanosecond timescales compress voids to quantum-relevant regimes. Some theories propose that vacuum fluctuations amplify emission or seed photon bursts. While controversial, such models suggest quantum energy interacts with collapsing bubbles. Casimir-like fields could enhance radiation from nanoscale voids. Even if not dominant, the overlap of quantum and acoustic domains is striking. Bubbles become laboratories for testing quantum vacuum physics. The paradox expands into sonochemistry and sonophysics. Sonoluminescent bubbles emit picosecond flashes of light far hotter than surrounding liquids. It is like squeezing darkness until sparks of light appear. Skeptics argue that bubble stability can be explained without invoking quantum vacuum. Hypotheses include gas supersaturation, surface pinning, contamination, or dynamic influx. These classical models address many observations without resorting to exotic physics. Yet gaps remain, especially in explaining hour-long persistence of surface nanobubbles. The difficulty lies in separating small Casimir contributions from dominant classical forces. Direct experiments at the nanoscale are technically demanding. Thus, the quantum explanation remains suggestive but unproven. The paradox survives in ambiguity. AFM studies attribute nanobubble longevity mainly to pinning and supersaturation, not Casimir effects. It is like attributing a mysterious sound to wind, though whispers of music remain unexplained. If Casimir force influence bubbles, they become tools for nanotechnology. Engineers could exploit vacuum stabilization for drug delivery, catalysis, or energy harvesting. Nanobubbles might act as quantum-enhanced reactors for chemical reactions. Control of quantum vacuum contributions could tune lifetimes and properties. Devices could emerge that use Casimir pressures for nanoscale actuation. This would merge fluidics with quantum electrodynamics. Applications would grow from paradoxical physics. Mystery becomes opportunity. Nanobubbles and catalysis accelerate oxidation reactions, possibly aided by unconventional stabilization. It is like harnessing the invisible wind to turn microscopic turbines. Resolving the paradox requires targeted experiments. Precision measurements of bubble lifetimes, sizes, and forces must be compared with quantum models. Casimir contributions could be tested by altering materials or dielectric environments. Microgravity, vacuum chambers, or ultrapure liquids may help isolate effects. Advances in AFM, high-speed optics, and spectroscopy provide new tools. Experimental confirmation would revolutionize both fluid dynamics and quantum physics. Until then, the hypothesis remains tantalizing but speculative. Testing the boundary is science's path forward. Experiments with hydrophobic vs hydrophilic substrates could reveal Casimir-dependent stability differences. It is like adjusting mirrors to see if light bends in ways predicted by hidden theories. The paradox is that quantum vacuum fluctuations, forces born of nothingness, may influence ordinary bubbles in liquids. Classically unstable nanostructures persist in ways that suggest invisible support. Yet the same effect can also destabilize films, creating fragility instead of longevity. Stability and instability coexist in the same quantum field. Do microbubbles live partly because of vacuum physics, or are classical explanations sufficient? The Casimir bubble paradox highlights the difficulty of separating scales in nature. At the boundary of fluid mechanics and quantum electrodynamics, bubbles whisper secrets of the vacuum. A nanobubble lasting for hours on a surface may be both a classical anomaly and a quantum experiment. It is like discovering that shadows themselves can hold up walls.